Hey, AP Chemsters, this is Mrs. Vanderbilt bringing you the part 2 edition of the Blankwalle of 14.7. We left off with question number, I believe, 20. So, okay. Hey, AP Chemsters, this is Mrs. Vanderbilt bringing you another edition of the Blankwalle series. We have left off with problem number 20, so let's begin with problem number 21. This says the reaction quotient for the system is 7.2 times 10 to the second. Hopefully you can do that math in your head and you say it's 720. If the equilibrium constant for the system is 36, what's going to happen as the equilibrium approached? Well, what are you going to do in order to answer this question? You need to compare what two numbers? Hopefully you thought, I need to compare the reaction quotient right here, 720, with the equilibrium constant of 36. So your Q is bigger than your K. So if Q is bigger than your K, now what? We got to get Q to get smaller, don't we? So if Q gets smaller, I guess I'll put it down here. If Q gets smaller, you need less products. And there should be an R here, so you need more reactants. So how are you going to get more reactants? You need to shift it to the left. So that's all you need to say. It's going to shift to the left. Now, what answer here would tell me this? Does anything here say you need to lose products? No. Does anything here say you need to make more reactants? Letter B does. So let's circle letter B. Letter B is actually the right answer. There will be a net gain in the reactant. Now, I just want to look real quick at letter E. Letter E is obviously wrong, but let's take a look at it anyway. It says the equilibrium constant will decrease until it equals the reaction quotient. I hope you recognize how wrong that statement really is. Will the equilibrium constant ever change? No, that's why they call it a constant. It doesn't change. Not with the conditions we've set up. We are going to find out that once again the constant will change with a change in temperature, but not just with this setup here, no. So hopefully you recognize that this was a really wrong statement because the equilibrium constant will not change. It will not shift to equal the reaction quotient. It's the other way around. The reaction quotient is going to have to shift to meet the equilibrium constant. So hopefully that made sense. Why don't we go ahead and turn the page and let's look at problem number 22. All right, so the problem number 22 is actually quite similar. And here we have the reaction of 2HF making hydrogen gas and fluorine gas. Oh, and I also gave you the K is 0.01. I know it's in scientific notation, but it's 0.01. Now look carefully at the next part. So it's given 1.0 mole, 0.328 moles, 0.750 moles. What do you recognize with the idea that we have moles? Can we have moles? And the answer is not in the Q, not in the K. What needs to be in those equations is molarity. So we need to convert these ideas of moles into molarity. So why don't you go ahead and kind of rewrite these things as molarities. Take a minute, pause this, and come back when you're done. All right, so hopefully you know, here's my my equation. I put my two reactants over my products. So what do you have to do with your products? You have to square it because the coefficient here. And did you get these values for the molarity of the system here? You had to convert your moles into molarities. And then when you do this math, I'm hoping that you get this number. And by golly, if you look closely, that is answer B. So that would be the reaction quotient here. Now, once again, they're asking you, well, which way will the system shift? Compare our Q with your K. Remember, this is 0.01. This is 0.24. So what's happening? Q is what? Greater than or less than K? Hopefully you got Q is greater than K. So what does that mean? You have too much products. So what is the system going to do? The system is going to reduce the amount of products and increase the amount of reactants. So what does that mean? If you increase the amount of reactants, it's going to shift to the left to create more reactants. So we're going to make the products to make more reactants so that Q will lower until it equals K. Okay, why don't you go ahead and let's look at problem number, what is this, 23. This is our last problem. So problem number 23 says the synthesis of ammonia, I'm going to kind of scoot this up a little bit, there you go. At 500 degrees, the equilibrium constant is, there it is, 0.06 or 6.0 times 10 to the negative 2. Predict the direction which the system will shift to reach the equilibrium. Well, wait a minute. Did the problem tell you our equation? Because we have to know the equation, don't we? We have to know the equation so we can set up the K and the Q values. We have to know if we have to square anything or cube anything. So we need to know what the equation is. Well, we're going to be making ammonia. And hopefully you remember that ammonia is NH3. It's an equilibrium, they tell us, because there's an equilibrium constant. So I'll put those there. So what sort of things make NH3? Well, I'm hoping that you recognize we need some nitrogen gas. Anything else? Oh, yeah, hydrogen gas. Okay. So we know we're going to have to add these two together, but what comes next? Hopefully you know you need to balance it. So go ahead and balance this for a second. All right, did you put a 3 here and a 2 there? So do you see why it was so important to be able to balance that? You have to write the equation and balance it before you do this. So, all right, what are we supposed to do here? We're supposed to determine which direction the system will shift given these sets of circumstances. What do you need to know here? What do you have to solve for? Whenever you are asked to predict the direction that the equilibrium will shift, you must solve for Q. Folks, you're going to have to know how to do this in future chapters. I believe probably chapter 16, you're going to have to understand the idea of Q once again and how things are going to shift based on your Q value. So this doesn't go away. Get used to the idea that, oh, I need to find Q if I need to know what direction things shift. So because of our balanced equation, here is my Q value. Notice how I had to square ammonia. I didn't have to do anything to nitrogen. I had to cube NH3. Fortunately, problem number 23, these are already in molarities, so I don't have to do anything funky with them. So I'm going to just plug in my values. So why don't you pause this and come up with your own math and see if you get what I get. All right, well, this is what I get. I sure hope I'm right. I didn't check my answer, but I know it's going to be a big number because I recognize this is going to be to the 3 to the negative 3 is negative 12. So this is a negative 17 right here. This is a negative 6. So I know at least I know it's going to be a big number. So hopefully that's right. And what do you notice? This is a huge number. This is like what? I don't know, 12 million or something. And that's a huge Q. Compare it to this number. Here's my K. That's 0.06. So which is bigger, Q or K? Hopefully that's a no-brainer. Q is much bigger than K. So what do we have to do? We have to lower Q. We've seen this before. How do we lower Q? We have to make the products smaller, the reactants bigger. So we have to reduce P, increase R. So your answer here is predict the direction in which the system will shift. We're going to shift to the left so that we make more reactants. So this is going to be a shift to the left. Why don't you go ahead and write that down. All right, for part B, hang on a second. Sorry about that. I wanted to scroll it down to give myself a little more room here. We're dealing with the same equation again. So we still have to square ammonia, cube hydrogen. And this time we're going to plug in some different numbers. So we have some different concentrations. And so here are those values. Why don't you pause this for a second and come up with your own math. Be very careful when you cube things. Watch how you put it in your calculator. Perhaps it might be a little more beneficial to type this in as 0.354 cubed instead of maybe using your exponent, your E button, because you're probably going to have to use your caret button as well. So go ahead and try this, pause this, and see what you get. All right. See how you did. This is what I got. Oh my goodness. Take a look at this number. Take a look at this number. Here's my Q. Here's my K. This is really 0.06, right? 0.060. This is 0.0601. What is this really close to, if not exactly on? They're equal to each other. So what does that mean? Q is equal to K. Go back and look at that picture that we had on the second page of this 14.7. You're at equilibrium. Is it going to shift anymore? Yeah, this is the picture I wanted you to see. This is where Q is equal to K. Do we need to shift one direction or shift another direction? No, you're there. There is no shifting. You are already at equilibrium. So there is no shift. Let's go back to the problem again. Okay, finally part C. We have a new set of conditions. Let's see what happens here. Here's Q again. Plugging in the values. I'm just putting the numbers here. And again, pause this, see what you get. See if you get what I get. All right, how'd you do? I got 0.002. Compare this to my equilibrium constant. Hey, I'll just use this number up here. So what is this case? Q is smaller than K. So that means we need to make this a bigger number. That means we need to make this a bigger number and this a smaller number. I need more products to make this a bigger number so that it reaches K. So how am I going to do this? How do I make more products? It's going to shift to the right. So why don't you write that down? This will shift to the right. And really, that's everything. I hope this was helpful. We're going to begin or probably talk about section 14.8. We're going to use, I believe, the ICE tables one more time. And actually, we're almost done with this chapter. So hang in there. Hopefully that helped.